All right, so the first problem set is now available for download, so come and get it. As I say, we have our problem session tomorrow at 9 a.m. So I'll see you there. So I'm going to be actually, unfortunately, away on Wednesday next week. So I'll have my office hours on Monday next week. We still need to figure out a time when I'm available and you guys are, and I will eventually have today. So we have a little doodle poll or something equivalent. All right, we'll get that together. All right. Okay, so last time we basically just set the stage by writing down Maxwell's equations. Now, to my horror, I actually wrote down Maxwell's equations incorrectly at the end of the last lecture. God, I'm aware of what could run on such a Not, don't fire me yet, but soon. But these are correct. In any event, one of the things that we were talking about that's important is that there's kind of two different languages that are spoken in how we write down Maxwell's equations, and it all has to do with how we decide to express the units of charge and current in terms of mechanical units. Okay, and these are the two basic choices. This is the sort of most general form that we could write Maxwell's equations in, with some choices of these constants, K1, K2, and alpha that were defined last time, which relate to, Coulomb's law, the Biot-Savart law, and basically Faraday's law. And they determine how we specify charge and current relative to mass, length, and seconds, and how we relate electric and magnetic fields. We have arbitrary choices to do that, okay? The System International, these are Maxwell's equations as you probably are most familiar with them, the differential form, which have these epsilon knots and u knots in them, okay? They're radicalized MKS because they get rid of the 4 pi's that appear naturally in the equations, which have to do with 4 pi steradians, and it's because you didn't want to carry them around. That's why the 4 pi's are there. The epsilon knots and u knots are really vestiges of the ether. These are the equations in Gaussian CGS, which are my preferred set of units and the ones that you're stuck with learning with me. And one of the nicest thing about Gaussian units is that the electric field and the magnetic field have the same units, okay? So, as we were discussing, it's a lot easier to just even do dimensional analysis when looking at the equations and just seeing that the units on both sides of the equation are the same. Okay, so we'll get used to this, I hope, but there are just sort of some tricks to the trade. All right, very good. So let's see. So to just sort of get started here, when we're dealing with electronic, yes?
I had a quick question on Gaussian. Should the alpha be C since it's 1 over alpha?
Oh yeah, you are absolutely correct. You are correct. Thank you. Yes, thank you. Okay. So when we are working with, and we're going to do the analysis associated with thinking about electromagnetic fields, there's lots of vectors around. And as we will see also, the generalization tensors. So we're going to just get started here by just thinking a little bit about how we are going to describe them, these mathematical objects, and be able to try to manipulate them in ways that are perhaps more efficient and ultimately easier than ways that you might have learned in your undergraduate studies, okay? So for today, we're just going to do a quick breeze through talking about vectors and tensors and notation. Okay. Yes?
For the Gaussian Ampere-Maxwell equation, it's supposed to be 1 over c squared for the time derivative of the E field?
No. Where are we here?
The bottom equation for the Gaussian.
This one?
Yeah.
No, it's 1 over c because we got an alpha times a k2 over k1.
Okay, alpha. Okay.
Yeah, yeah. And the reason we know that it has to be that is that the units are right. Because c times t is a length. And the gradient is a 1 over a length. And E and B have the same units. So clearly that's correct. A good way to check. Everyone see what I just did? Okay. Okay, back to this. The whole way vectors and tensors are defined is firstly thinking about position. And the position in 3D space, as we will think about it, we'll call x. And that's the position vector, okay? And we have a reference frame. Which, when we have a vector space, the reference frame defines a basis in which we can express the vector in a coordinate system. So the reference frame determines coordinates. Okay? And we can call these the basis vectors. I'll use the notation. If it's a unit vector, it has a little, it's called E. So sometimes I'll put a hat on it, but hats get me confused because I work in quantum mechanics and hats are operators and transmit that, so we won't use hats, okay? So this is our coordinate system, and we often also label these as with the index 1, 2, or 3. Yeah.
I think 2, I don't think you have an E.
Z, yeah, sorry. Thanks. And so we have, this is our coordinate system, and we have some vector in here which has projections on all of these axes. And so we can write the vector as being represented by, and I'll use this little notation as a dot, represented by these coordinates. Okay. Said another way, the vector is equal to a linear superposition of the basis vectors weighted by the coordinates. Okay. Which is the sum of the coordinates that weight the basis vectors, okay? Now, often, and this was developed first by Einstein, and so it gets his name, instead of writing out this sum, we can save some work in terms of all these sums and things by using what's called the Einstein summation convention. And write this like this. And the convention is that if you have a repeated index, you sum over it. So the fact that I appears twice tells you that this means I should sum over all the possible values that I can take, which in this case is 1 to 3. So this is just a shorthand, and it saves us a lot of dealing with complicated vector and tensor equations, the summation convention. Yes, sir?
My question is, how do we know that we need to use Einstein summation conventions?
We always do. So if we're working with this, we all agree we're going to use the summation convention, and whenever we see a repeated index, we sum. That's how we know, because we've decided beforehand. That's what we're going to do. And we'll have practice doing it. Very good. Now, this is more than just a vector space, the space of positions. It's also an inner product vector space. So we have an inner product defined on the vector space. And in order to define that inner product, we have to define what the inner product is between two basis vectors, okay? So this inner product is the dot product. And when we have Euclidean space, then these vectors are orthogonal. And we choose them to be orthonormal so that this is written as the Kronecker delta where this symbol means it's 0 if I does not equal j and 1 when I equals j. Okay? So that is a structure that we impose on the vector space. Okay, so this is a Euclidean space when it has this inner product. Okay. The other thing about the dot product is that it's linear. And what that, of course, means is that if I look at a linear combination of two vectors, say xa and xb, with two coefficients. So this is, if it's a vector space, I can take a linear combination thereof. If I look at the dot product of this with some other vector, then I can just distribute it through linearly. That's what it means to say that the dot product is a linear operation. Okay? Something I think we're all quite familiar with. So now we can get a little bit of practice just using the Einstein summation convention and just reminding ourselves of some very basic things. So if I look at the dot product of the position vector with itself, I can write that in terms of its superposition with the basis vectors divided into itself. Now, here's the first and most important rule in how you deal with Einstein's summation conventions. And that's the idea of a dummy index versus a fixed index, okay? This index, I, we call a dummy index because it's summed over. It doesn't matter what I chose. I could have written J there. I could have written K. I could have written smiley face. It wouldn't matter. Whatever I choose, it doesn't matter. It's gone. I've summed over it. This thing doesn't depend on I. I doesn't appear on the left side of the equation. So it's a dummy. It's just a placeholder that I'm summing over. But once I use one dummy index, I don't use it again. Okay, so I should not write this because this is not sum with that, right? I can't use, once a dummy index is used, you've used it up. You can't use it again. Don't use it again. So now pick a different one. I'll call it J. Okay? That's the most important rule in how you deal with the summation convention is don't reuse your dummy indexes.
I think students have a problem with that.
Oh, I do. Everyone does. It's a problem. Okay? So let's continue. So this is xi, xj, using the fact that this is linear, ei dot ej. Just using the linearity. Yeah.
So usually when I've seen Einstein summation notation, it's with one in the subscript and one in the superscript. Is that just a thing for higher dimension?
No, that is when you have a non-Euclidean space, then you have to be very careful. And we will talk about that in the semester when we start talking about Minkowski space, and when we talk about space-time. Minkowski space is not Euclidean space, and because of that, there's a difference between what are called covariant and contravariant vectors. But when we're dealing with Euclidean space, that's heavy-handed. There's no reason to have upper and lower indices. It's pedantic. I'm pedantic enough. You don't need more. All right. So ei dot ej, we said, is delta ij. Okay? So now we see here we have the summation. This is summed over both I and both j. So we can do the sum over one of those. Let's say if we sum over j, whenever we see a Kronecker delta, what it tells us is to replace this index with that one. Because the only time this object, this number, is non-zero is when I equals j. Otherwise it's 0. So doing the summing over j means replace j by I. That's what we do when we see a Kronecker. So this then becomes xi, xi. Which of course, I'll then write out explicitly as x1 squared plus x2 squared plus x3 squared, which is the length of the vector squared by the Pythagoras theorem. So the length squared of the vector is the sums of the squares of its components, right? Very good. All right. Let me just remember where I was headed with this. Okay, good. So, very importantly, in thinking about any of this, is the whole notion of a change of the reference frame. Which I can also think about it as the change of the basis. Okay? Yeah.
So, coming back to the rule you mentioned,
Uh-huh.
do we only ever have an index show up twice in an expression? And after twice it's used up?
That's correct.
Okay.
That's correct. The summation is only over 2 indices. Period. Yeah. Right, so, let's say we have our basis, E1, E2, this is our reference frame. And we go to it, we think about the representation or the coordinates of position in a different reference frame. In particular, let's consider a rotation. Right? So let's say that I rotated by some angle theta around the z-axis, so that this is my new E1, I'll call it E1 prime, this is my new E2, E2 prime, and I'll keep this fixed. Okay? Or if because I have a hard time drawing perspective in the XY plane, I have these new bases, okay? So the new basis vectors live in the vector space and thus can be expressed as linear combinations of the old basis vectors, right? So the basis vector is some linear combination of the original basis vectors, and I'll call that the coefficients, right? Such that Rij is just the component of the new basis vector with respect to the old basis vector. Yes?
Is there a sum there, or you?
There is.
There is, okay.
There's always a sum because I have a repeated index. So whenever we see a repeated index, we have a sum. Okay? Everyone clear? So this is just a re-expression of these things. And so, you know, in this case, E1 prime is equal to cos theta E1 plus sine theta E2, just by the dot products. And E2 prime is minus sine theta E1 plus cos theta E2, and E3 prime is unchanged. Okay, so that's a particular. This rotation tells me a particular way of changing the basis. Okay. Now, and so in this case, I have these R's make up elements of a matrix. And I can think about that matrix with rows and columns, the first index being the row, the second index being the column, such that R matrix, I'll use the double bar to represent this as a matrix, is very good. Now, as you know, there's an important property of this particular matrix or change of reference frame transformation in that if I do a rotation, I preserve the inner product, okay? So rotations preserve the inner product. That is to say that the new basis vectors, after I have rotated the reference frame, have the same inner product as the original one. That's what it means to say I preserve the inner product. Whatever the inner product was of the basis vectors is the same, which is delta ij. But this is equal to ri. Okay, now what letter should I choose? K is a good one. Ek dotted into RJLEL, right? Which is equal to the dot product of this with this is a Kronecker delta. So this is RIK RJL delta KL. Everyone clear? I want to emphasize one point here. These objects are numbers. Thus they commute. I can write them in any order. They are the elements of a matrix. The matrices don't compute. They don't commute, but the matrix elements are numbers, and I can write them in any order I like. Okay. And so I can now do the trick. I sum over one of these indices, and I get RJK. And that equals the Kronecker delta. Okay? So what does that tell me? Well, this looks like matrix multiplication. Let us remind ourselves about, just very quickly, the rules of matrix multiplication. If I have two matrices, say A and B, and I want to multiply them together, and I want to say what is the element of the multiplication, then what this is equal to is I have to sum the row of this with the column of that. Sum over K. Does everyone see that that is actually matrix multiplication? Because you're summing a row with a column, right? That's how I do it in my head. I take the column and I shove it on top of them and multiply them together because I'm a visual guy. And that's what this is, right? So that's matrix multiplication. But this is not, I'm summing the row with the row rather than the column with the column. So what this is R IK times R, the kjth element of the transpose of the matrix. The transpose of the matrix is the matrix that switches the rows and columns. Okay? So this object is equal to R times R transpose Ij is equal to delta Ij. That's what we just proved. So because the rotation preserves the inner product, what it tells us is that the rotation matrix is an orthogonal matrix. And to be an orthogonal matrix is to say that the transpose of the matrix is the inverse of the matrix, because if it's this object is the elements of the Kronecker delta are the elements of the identity matrix. They are only, if I thought about the Kronecker delta as the elements of a 3x3 matrix, then the only non-zero elements are on the diagonal. And so the Kronecker delta are the matrix elements of the identity matrix. So what this is telling me is that when I multiply R by the transpose matrix, I should get the identity matrix. And thus, the transpose is the inverse. And that's what makes it an orthogonal matrix. Thomasson question?
So we started with the dot product expressed in the summation notation. Then we got over to, we had the Kronecker delta times the two coefficients. And
Uh-huh.
then
Then we summed over L.
right, and then far right hand side, we got Kronecker delta out.
No, that's because of this. The Kronecker delta came because I claimed that the rotation matrix preserves the inner product. And because it preserves the inner product, the dot product of the new basis vectors is the same as the dot product of the old basis vectors. But the dot product of the old basis vectors was the Kronecker delta because they were orthogonal.
Okay.
So that's why I said that equal to the Kronecker. Thank you. So that's a property of a rotation matrix, is that it's an orthogonal matrix. Okay. There are two kinds of orthogonal matrices, and what they're called proper rotations, and I don't know if they're improper, but anyway, or if something else. So let's maybe I'll write it over here. If I look at the determinant of R times R transpose, well, that's the determinant of the identity. And what's the determinant of the identity? 1, right? Because I multiply all those guys together. But the determinant of the product of matrices is the product of the determinants. Okay? But the determinant of the transpose of a matrix is equal to the determinant of the matrix itself. So it doesn't matter, I transpose it, it won't change the determinant. And thus, this is equal to the square of the determinant of the rotation matrix, which has to be 1. Okay? And so from this, we learn that for orthogonal matrices, there are transformations that preserve the inner product that the determinant of R has to be either +1 or -1. Okay? Because its square is 1. It could be -1. Now, if the determinant is 1, we call that a proper rotation. Like what we just described, rotation around the z-axis by some angle. Okay? But we can also have orthogonal transformations that are not proper rotations, and those are parity inversions. So for example, the transformation that says takes E1 to E2 and E2 to E1, but leaves E3 alone, is a reflection of sorts that will give me a -1. Okay? Or there are many examples. I might have just say E3 goes to -E3, and E1 goes to itself, and E2 goes to itself. That's obviously a inversion which has determinant -1. This preserves the inner product, but it doesn't preserve, doesn't preserve the determinant. It's not a proper rotation. We'll come back to that in terms of our definitions of vectors, etc. Okay, very good. So now I want to talk about the idea of how we've talked about how the basis vectors change. I want to talk about how the coordinates of the vector, the components x1, x2, and x3, change under rotations. Okay. And there are two kinds of rotations, and this always gets confusing, I think. There's what are called passive rotations. And in this case, what I'm doing is I'm changing the frame of reference, but not changing the vector itself. So let's just look at this in 2D, because God knows I have a hard time drawing in 3D, where I have some vector x, okay, in this plane. And now I have my new basis. I haven't rotated the vector, I've rotated the coordinate system, okay? And I can ask, what are the coordinates of this vector in the new frame? But the vector is the same. I'm just looking, it's two different representations of the same vector. So I could say x has some coordinates with respect to the original basis and some coordinates with respect to the new basis, but it's the same vector. It sums to the same thing. And ask, how does x prime relate to x? What is the transformation I need to do in order to relate the coordinates in the new reference frame to the coordinates in the old reference frame? That should be distinguished between what's called an active rotation, where what I'm doing is keeping the basis fixed, but rotating the vector itself, okay? In which case, these are two different positions. One's the rotated position. I've actively changed the position and asked how this guy, what are its coordinates with respect to the original, right? These are two different vectors because they're two different superpositions. So this is the active rotation and this is the passive rotation. Now, clearly they're related to one another because one is kind of just the inverse of the other, right? If I rotate the coordinate system the other way, it's as if I rotated the vector forward. So they're related to one another, but it's always confusing because when you write down rotation matrices, it's not always clear, are we talking about the passive rotation or the active rotation? So let's just write down what those things are. Let's look at the passive rotation over here. Fixed position, change reference frame. Okay, so we have xi equals ei, xi times ei, that's my vector, is equal to that. But this is Ri. Ij Ej by this definition of R. Okay? So this tells me that x, the components, the jth component of the vector is equal to xi prime r I rj. Does everyone see what I just did in this sleight of hand? Why this was xj? Because I've summed this over I, okay? So I could ask xj is equal to the dot product of this, okay? And then when I pick that off, I get this term. Let's see some puzzle faces out there. You can always check that I've done this right because there is a dummy index and a free index or a fixed index. Here I have summed over I. It's gone. Once you sum over it, it doesn't depend on it. But J is a free index. That's to say, it's not summed over. And this is the one that's picked off. Okay. Very good. So what this tells me, again, I can rewrite this as matrix multiplication. I think it as a matrix operating on a vector. Okay, what did I do? I rewrote this as Rij xi prime. That's because these are numbers. I can put them on any side I want. So this number times this number is this number times that number. But here I'm not summing a column with a row, so I flipped the indices and wrote it as the transpose of the thing in the other direction. Tricky? Does anyone understand? Yeah.
So, I'm sorry, I'm still back with the x sub j part here.
Yeah.
So, I'm wondering, is that Rij, it's literally just the same one as,
Yeah.
same one as over there.
Yeah.
So the only thing that you're changing is you're rewriting that little part over here as x sub j.
Yeah. So this is the jth component in the old basis.
Yes, I agree.
Yep.
Okay.
That's what this is. Good. So, no, this should be a prime. So now I can relate this for a passive rotation. What it says is that the coordinates in the new basis, or the new reference frame, are related to the coordinates in the old reference frame through the following relation. Let's see, sum over j. So this is a generic thing. It says if I have a change of basis, and I've done a passive rotation, it says I'm keeping the position fixed, I'm just asking what its coordinates are in the new basis, then what I have to do is multiply it by the inverse of the transpose of the matrix R, defined as the thing that changes the basis vectors. Now, for an orthogonal transformation, the transpose is the inverse. So for Euclidean space, we get that in a passive transformation, the coordinates transform exactly the same way as the basis vectors do, according to this same matrix. Yeah.
Is there a distinction between normal R and boldface R?
I'm being sloppy.
Okay, so no.
I'm using boldface R when it's the matrix and unboldface when it's the number.
But even
Okay.
though it's a matrix, it still has the subscript side change.
Yeah. I mean,
Okay.
don't get obsessed with it.
Okay.
These are the numbers.
Yeah.
Okay. Okay, so this is the important point. For a passive rotation, it's the same thing. Now we will see this a little bit. The reason I did this pedagogy here is that when we start talking about Minkowski space, this isn't going to be true anymore. And the things that transform, like the basis vectors versus the coordinates, are things that go with the basis vectors are called covariant. They go with them, and the things that go against them are contravariant. That's where the terms covariant and contravariant come from. So this is just a harbinger of things to come, okay? Right. Well, what about for the active transformation? For an active transformation, well, this is what we got over here. So we have that there are two different factors. I just don't confuse that one quick. Just take a break. Okay. Right. Okay. That's what I got myself figured out. So this vector is equal to what I get when I apply the rotation operator to x, because I'm actively rotating the vector. Okay? And so that's equal to the rotation on xi ei, which is xi r acting on ei, which is xi r ij ej, because that's the rotation acting on that. That's ei prime. And so what I see here is the relationship for an active rotation is the following. In an active rotation, the coordinates of the rotated vector are related by the transpose. This is the transpose acting. The transpose is the inverse, and thus, as we were saying, the passive and active transformations are just sort of inverses of one another. Yeah?
Excuse me, I thought like in active rotation, we're not rotating the basis. What?
Okay, so let me try to explain this more carefully. Here's an active rotation. I'm not changing the basis, and this was the original vector, this is the rotating vector. But now I'm asking the following question. How are the coordinates of this rotated vector related to the coordinates of this vector in the same basis? So I say x was an original vector and it had coordinates with respect to the original basis. X prime is a vector and it also has coordinates with respect to this. There are two sets of coordinates with respect to the same basis. And I'm asking how are these coordinates related to those coordinates? And the exercise below showed me how those coordinates are related. That's what this is. I haven't changed the basis, I'm just asking what are the coordinates of the new vector with respect to the old basis. And what we find is it transforms according to the transpose, which is this. Now, if you go to Wikipedia and you ask what is a rotation matrix, this is what you'll find. Okay? So just want you to be aware, you have to understand, are they talking about an active rotation or a passive rotation? In Wikipedia, they're talking about active rotations.
So it's different, it's the transpose.
Yeah. Yeah, the active rotation is the transpose of the rotation for a passive rotation. Okay? Yes, sir.
That rotation talk is only, like what you just said, the transpose thing. That's only true in like regular Euclidean.
That's right.
Space.
That's correct. And that's where we're going to be for the vast majority of this class. Yeah. Okay. Very good. So, with that said, we can then generalize from position to an arbitrary object that we'll call a vector.
It's a vector.
A vector is an object which transforms under rotations the same way that position does. Okay? So I can think about it as some linear combination of the basis vectors and the components under rotation it's also active, but would just be with the transpose. If I go to a different reference frame, any object that does that is a vector. So, for example, velocity is a vector. If I look at this, that's a vector. Momentum is a vector. What about angular momentum? Yeah.
Just double check, that's a passive rotation.
It is. That's, yeah. It would also be true under an active rotation, it would transform with the transpose. That would be totally fine. The R's I'm using here are the passive rotation matrices. Okay. Okay, now the next thing we need to remind ourselves about is the cross product. Okay, so the cross to deal with the cross product, we're going to introduce the Levy Civita symbol. Epsilon ijk, which is 0 if I equals j or j equals k, or k equals I. If any two indices are repeated, it's 0. It's 1 if I equals 1, j equals 2, k equals 3, or any cyclic permutation. So cyclic permutation means I permute 1, 2, and 3 in a cycle. So 3, 1, 2, or 2, 3, 1. Any cycle of this is 1, and it's -1 otherwise. So that means if I switch any of the two indices, I get a -1, and this is sometimes called the completely antisymmetric tensor. The term tensor will come to in a moment. All right, so with that, we define the dot product, the cross product, say, if I say C is defined as the cross product of A and B, then the ith component of this vector is the ith component of A cross B. And that ith component is found by epsilon ijk aj bk, summed over j and summed over k, because those are repeated indices. So for example, C1 is equal to, if I is 1, then j and k can only be 2 or 3, because if they're equal to 1, it makes no contribution because it's 0. So what I get is A2 B3 minus A3 B2, using the Einstein summation convention. Okay? And so the vector C is equal to the sum over I epsilon ijk, or I can write it this way, epsilon ijk e sub I a sub j b sub k. Everyone see that? Because I just put in the components and I move the things around. Now why did I do it this way? Because this may be, there's a relationship between the Levitshev symbol and determinants. So this is equal to the determinant of the first guy, and then the second guy, and then the third guy, written as rows in a matrix. And maybe this is how you learn to take a cross product. I don't know. But that's how they often teach it, so I take this guy, E1, and then I multiply this by this by this, and then I do this. But I have never, in 20x years, written a cross product as a determinant. We always just use the Levitshev symbol. As you will see, it is your friend. It's a little bit of a prickly friend. We all have some of them, but it is your friend nonetheless. Okay. So one thing I might ask is, so let's consider angular momentum. Is angular momentum a vector? Let me see what I want to say. I mixed it. Right.
This is
Okay.
actually cooler.
Yeah. Let's just go there. So let's say that we have L is position crossed into momentum. Momentum is a vector because velocity is a vector, and I can multiply by mass. Mass is a scalar, so it's still a vector. Okay? So let's think about the components of angular momentum. So what I need to do is apply the rotation to this, and what I'm going to get is epsilon ijk, the components of this, xi prime p, or xj prime pk prime. That's the rotated components. Let's see how this transforms.
Why are those the rotated components? There's no rotation matrix there.
I'm saying I've gone to a new reference frame. These are the components in a different reference frame, in the rotated reference frame. Okay, so I'm asking what are those components? All right. Okay, yeah. Oh, trickery. I forgot that. Okay, so let's go for this. So this guy, each one of these is a vector. So that's epsilon ijk, r j l x l, and r k n, or m p n. Those are the components in the rotated frame. Okay? The components on the rotated frame are given by the passive rotation. So now I'm going to play a trick here, and I'm going to insert the identity. So in particular, let us say that this guy is equal to njk delta in. That's why not? I mean, it seems why the hell would I do that? But okay. So this, though, is equal to, I can think about this as the product of, let's see, what indices do I want to use here? Oh, P, elemental P, times R transpose Pn. Because when I multiply this by its orthogonal matrix, that's the identity. So let's put that all together. Right. So when I do all of that, what I get is that the components of angular momentum in the new reference frame are equal to, let's see, we have an RIP, rest in peace. We have an epsilon NJK. We have an RNP. We have an RJL and an RKM. And then we have the two XL and PM. Just putting all the terms together there and taking the transpose. The transpose takes an entropy. Now, what the heck Now, this goes back to this determinant business. You go, I should have written this earlier, but if I look at epsilon ijk of the product of three vectors, u, v, w, that is the determinant of the matrix as I wrote it earlier, but now just for any arbitrary three vectors in a row, okay. So this is summed over I, j, and k. It's equivalent to that determinant.
Are those three different vectors?
They are u, v, w.
And which ones are being cross-producted together?
They're not cross-product together. This is just a summation.
Okay.
Okay, so I could think about it as the dot product of u with the cross product of v and w, if I wanted to, because that's what this is. But what I'm saying is just by the laws of the summation and the inversion, that if I take three vectors like this with three indices, and I sum them with the Levitida, it's equivalent to this determinant. Now, what we got here is exactly that. If I just think about the sum over n, the sum over j, and the sum over k, the p, l, and m are just some index. And this thing, thus, is equal to epsilon p, l, m times the determinant of this matrix. Hey, you'll have to think about that a little bit. But here's the bottom line of it. What do we get? We get the determinant of R times RIP epsilon PLM XLPM. This P has nothing to do with that P, excuse me. Okay? One is momentum, one was an index, but say like it. Yes?
I'm a little confused how that, I see where the determinant thing is, but
Yeah.
I'm a little confused how you then pull out that PLM. I don't exactly see how.
Where it is, it's because of the fact when I have to write these as, these are columns of the matrix,
Yeah.
that's where this additional epsilon PLM comes from.
Is that
This
just
is-
something we should like?
You should just work it out yourself, work it out yourself. But I want to come to the bottom line of it. The algebra, yeah, we gotta follow it, we gotta do it, but let's just think about what we ultimately say. Let's take a look at this expression. What is this? Well, this is the p component of angular momentum. Right? Because I'm summing over L and M, so this is the p component of x cross p, which is the p component of angular momentum. So what we have shown is that if I change the basis, if I look at the components of angular momentum in the rotated frame, its new components are related to the old components by this rule. And now I'm just gonna, doesn't matter. I could call this anything, it's a dummy index.
Isn't the determinant of a rotation gonna be unit?
Yeah, so this is sort of the point. If this is a proper rotation, if the change of base is a proper rotation, this is 1. So my question to you and everyone else is the angular momentum as defined by this cross product a vector or not. I defined a vector as an object that transforms a certain way under rotation. We defined the vector as an object that when I go to the transformed frame, it transforms according to this rule. Does angular momentum satisfy that? The answer is yes, if it's a proper rotation, but no if I do a orthogonal transformation that's a parity inversion. I could think about that. And vectors or objects that don't transform the same way under parity reflections as they do under rotations are called pseudo-vectors. Okay, so that was the point of this exercise. All right, I want to say then now a few words about tensors.
Excuse me, sir.
Yes, I'm listening.
It's not bad.
Oh, you want to take a picture of this? Okay, well, I will continue here then. But you know, all of these things are recorded, so you will be able to see them and you take a screenshot from your computer. It's the modern world. All right. A tensor is a object that transforms according to certain rules under rotations. Okay? So I can have a rank K tensor is an object that has K components, or K indices. So I have T, the tensor is Ti1, Ti2, dot, dot, dot. And these are the coordinates of the tensor with respect to a basis. So I can think about the thing, and we could write it as a evil double-headed arrow guy as where this is known as as opposed to the inner product, this is the outer product. So this is a tensor, and it transforms such that because of the way the basis vectors transform, the components of the tensor transform just like the basis vectors. So in a new coordinate system, T in the new coordinate system is related to the components in the old coordinate system by the application of a series of rotation matrices. summed over, oh no, this is J. Summed over repeated indices. So I rotate sum over this index, sum over that index, the third index, up to the kth index. An object that transforms in that way is a tensor. This is a ranked K tensor. What's an example? For example, if I think about rigid body motion, then we may have seen the moment of inertia tensor. Let's just write that down and then we'll conclude for today. So let's say again I have my friend angular momentum, but now I have this sum I'm going to write explicitly. This is not the coordinate, this is a particle. I have n particles that are, this is the sum of the angular momentum of all the particles, okay? Which I'll write then as mass of the particle times its velocity. Okay. Now, if this is a rigid body, like a top or something that is rotating, then I can think about the velocity in terms of the angular velocity. Okay. Now, I realize I skipped something, well, maybe we'll talk about it in the problem session. How do you do a triple cross product or two cross products? Well, you would use the rules of Levitsheva's to sum. And this is equal to omega times this dot this minus that.
Why doesn't the omega have an operator?
Because it's a rigid body and everything is rotating together
Okay.
in this case for a rigid body. So what we see here in this problem is that this is equal to an object that I can call the moment of inertia tensor dotted into the angular velocity, where this object is equal to the following. It's equal to the sum over the particles, the mass, the identity tensor, minus times the radius squared, minus the outer product of the position with itself. When I take the dot product of this tensor with that vector, I get this, because I get the identity here, and I get the dot product acting on this. The moment of inertia is an example of a rank 2 tensor. And what the moment of inertia tensor tells us is that the direction of the angular momentum vector is not necessarily the same as the direction of the angular velocity. If this were a scalar, then this would look like L equals I omega in the same way that P equals mv. But the moment of inertia is a tensor. It means you push on it one way and it goes the other way. Yeah,
So when we place two vectors next to each other, we mean the outer product?
that's what we mean.
Okay.
Yeah, when there's no dot, it means the outer product. Yeah, this is what's called a dyadic. So it is a fairly standard convention. So this is a geometric object, and the components of this is xi times xj. So this would say that the first thing, if I look at these components, these I can arrange in the same way that we arrange the components of a vector in a column. We can arrange the components of a rank 2 tensor in a matrix. All right. So we'll leave it there for now. In our homework, we're going to have some practice using Einstein's summation convention. There's one particular little rule that I skipped over that I forgot to discuss, but it's in the notes, and we'll discuss it more in the problem session tomorrow. All right. Have a good rest of the day, everybody.
Yeah.
Do you remember
It's the same time.
It's not 8:30 a.m.